Okay, so think about this for a second. What if I told you there's a secret language, a code, that explains how to build everything? I mean, everything from the water you drink to the phone you're probably holding right now. Well, that language is chemistry. And today, we're going to crack that code. We're starting with the absolute basics. Chemical formula.
So, have you ever followed a recipe to bake a cake or cook dinner? Chemistry works in pretty much the exact same way. A recipe gives you the ingredients, right, and the amounts you need? Well, a chemical formula is basically just that. It's a recipe, but for a single molecule. It's our instruction manual for building the universe.
So, to put it officially, a chemical formula is that recipe. It shows you the exact ratio of elements, the ingredients, that you need for one single unit of a substance. It's super precise. It tells you exactly what's in there and exactly how much of it. All right, section 1, decoding the language. Before we can start writing our own chemical recipes, we've got to learn how to read the ones that already exist. So let's get into it. Okay, let's just focus on the big examples here, CO2 and H2O. It's actually really simple. The big letters, those are the symbols for the elements. You'll find them on the periodic table. C is for carbon, H for hydrogen, O for oxygen. And that little number at the bottom right, that's called a subscript. It just tells you how many atoms of that element you've got. So for CO2, that means 1 carbon atom and 2 oxygen atoms. Simple as that. But wait, you might be wondering, what happens when you just have 1 atom? Look at this formula for sodium hydroxide, NaOH. You'll notice there are no numbers. That's not a mistake. It's just a little shortcut chemists use. If you don't see a number, it's an invisible 1. So there's 1 sodium, 1 oxygen, and 1 hydrogen. Okay, quick pop quiz for you then. Based on what we just learned, what atoms are in 1 molecule of NaOH? Pause and think if you need to. You got it right. There's Na, which is sodium, O for oxygen, and H for hydrogen. And because there are no subscripts, we know it's 1 of each. See? You're already decoding the language of chemistry. It's not so hard. All right, section 2, building with chemical Legos. So now that we can read the recipes, it's time for the fun part. Let's become the chefs. We're going to move from just reading formulas to actually building them from scratch. And honestly, the best way to picture this is to think about Legos. Seriously, imagine every atom is a Lego brick. You know how Legos have those little studs on top and holes on the bottom that let them click together? Well, atoms have something just like that, a special connecting power that decides how they can bond with each other. Now, that connecting power has a proper name in chemistry. It's called valency. It's all about how many hands an atom has to hold on to other atoms. But really, just think of it as the number of studs on that chemical Lego brick. If an atom has a valency of 2, it's like a Lego with 2 studs. It needs to connect to 2 other things. Get the studs to match up, and click, the molecule fits together perfectly. Now, don't panic. You don't have to memorize a giant list of these right now. The key takeaway is that this information exists in tables, just like this one. This is our builder's guide. It's our cheat sheet that tells us the valency or connecting power for all the common elements we'll be using.
So, how do we actually use this guide to build a formula? There's a really cool, simple trick called the cross method. It's basically 4 steps. First, you write down the symbols of the elements you're combining. Then, you write their valency number right above them. Step 3 is the magic part. You crisscross those numbers, bringing them down to become the subscript for the other atom. And finally, you just simplify the ratio if you can. It's a nearly foolproof way to get it right every time.
Okay, let's put this into practice. We're going to build magnesium nitrate. So we find magnesium, Mg, and its valency is 2. The nitrate part, that's NO3, has a valency of 1. Now we do the crisscross. The 1 from nitrate comes down to Mg, and remember, we don't write the 1s. The 2 from magnesium comes down to the nitrate. But wait, we need 2 of the entire nitrate group. That's where the brackets come in. We put NO3 in parentheses and the 2 on the outside. This tells us we need 2 whole nitrate Legos to click onto our 1 magnesium Lego. Section 3, from parts to products. So at this point, we can build the formula for just about any single compound. That's huge.
But what happens when these compounds meet and interact? That's the next step. We're moving from looking at individual ingredients to looking at the whole recipe, the chemical equation.
And honestly, you can think of a chemical equation as just one sentence. On the left side, you've got your starting ingredients. We call those the reactants. On the right side, you've got what you end up with, the final dish. We call those the products. And that arrow in the middle, it just means turns into or reacts to make. So here, sodium and chlorine are our reactants, and they react to make our product sodium chloride. That's all it is.
Section 4, the art of balancing. Okay, this next part is maybe the single most important rule in all of chemistry. It's a law of the universe. You can't create or destroy atoms in a chemical reaction. They just get rearranged into new patterns. It's like having a box of Legos. You can take them apart and build something new, but you still have the exact same number of bricks you started with. To make sure our equations follow this rule, we need one last skill, the art of balancing.
So let's look at a classic example, making water. Our reactants are hydrogen, H2, and oxygen, O2. Let's count the atoms. We start with 2 hydrogens and 2 oxygens on the left. But look at the product on the right, H2O. That's 2 hydrogens, but only 1 oxygen. So where did the other oxygen atom go? It can't just vanish into thin air. This equation is broken, it's unbalanced, and it violates that fundamental law.
The way we fix this is called balancing. And here's the golden rule. You have to remember this. You can never, ever change those little subscript numbers. Why? Because if you change H2O to H2O2, you don't have water anymore. You have hydrogen peroxide. You've changed the ingredient. Instead, what we do is add big numbers, called coefficients, in front of the whole molecule. This is like saying, okay, instead of 1 water molecule, let's make 2. You're changing the amount, not the ingredient itself.
And voila! By putting a big 2 in front of the H2 and another big 2 in front of the H2O, we get this. Now let's do the atom count. On the left, we now have 2 times 2, so 4 hydrogens, and 2 oxygens. And on the right, we have 2 water molecules, which gives us 4 hydrogens and 2 oxygens. Perfect match. The equation is balanced. The recipe is now correct.
So let's just take a breath and look at the whole journey we just took. This map lays it all out. We started with just the name of something, then we used our builder's guide, the valencies, and the cross method to write its formula. And finally, we put those formulas into a sentence, an equation, and then we balanced it to make sure we followed the #1 rule of the universe: you can't lose any atoms along the way. And just like that, you now have the key. You have the tools to decode the secret language of the world. Think about it. The process that lets plants make food, photosynthesis, that's a chemical equation. The way a bike chain rusts, that's an equation. The way your own body digests food, you guessed it, that's just a whole series of chemical equations. The code isn't a secret anymore. So I'll leave you with this question. What's the first secret recipe you're going to go out and decode?